I was invited to take part in a project to recalculate that depth. I'm going to talk a little bit about that. Here's what I'm going to talk about. I do have 2 slides that have math on them. I'll warn you in advance. They're not critical for the story, but they may help understand some of the bits. So overall, what we're talking about is data that came from this guy and this platform. There's the submersible limiting factor on the back of the pressure drop, which is formerly the NOAA ship MacArthur II, which is formerly the USNS Indomitable. So Victor Vescovo, that's the dude up there. Bit of an adventurer type. I think he climbed all the tallest peaks on the continents, had skied to the North and South Pole. I don't know how he got the idea to go dive all the deep parts of the ocean, but he did. Bought a ship, built a submersible, and set out to do it. One interesting thing, so said, all right, has anyone dove to the deepest part of all the world's oceans? The answer was no. But then the question, well, where are the deepest parts of the world's oceans? It wasn't exactly clear. And there's a good paper by Heather Stewart and Alan Jameson referenced here that went and dug through all the literature to try and figure out where all the deep spots are. It's a good piece to have in, our oceans are unmapped and unexplored. So they went and identified areas that were probably the deepest spots in all the world's oceans. They put a multi-beam on the bottom of the ship as well and surveyed all these places in conjunction with diving. UNH's own Cassie Bongiovanni was in charge of the mapping portion of this, and just recently published a paper here with that surveyed results. And so here's all the deepest spots in the world's oceans based on their survey work. And the blue here is the data the actual survey data. So again, this is probably not the crowd I need to tell that the oceans are largely unsurveyed, but this is a great example. In any case, he did it. In 2019, they finished, dove the deepest spots, including the Challenger Deep. Here's Mr. Vescovo looking very happy after completing that work, and plenty of press. Right, first guy to do this, mission to the world's deepest oceans, and James Cameron threw in a bit of a claim that maybe you didn't get the deepest. So in any case, this I think spurred Victor to remount an expedition back to the Challenger Deep, and as part of that, invited outside participation to really validate what is the deepest depth of the ocean, how can we make that measurement. So in that process, I got roped in, and I'll talk a little bit about that process in the future. So before we do, just a backup to the Challenger Deep. The Challenger Deep is named after the HMS Challenger, which a rather famous expedition in the 1800s. It's really the first dedicated oceanographic cruise. It was 1870s. They went around the world and just happened to take a deep sea cast close to the Challenger Deep. They had no idea it was there, and recorded a depth of 8,000 meters, which is by far the deepest depth ever observed in the oceans. Another HMS Challenger went back and did a series of both echo sounder and explosive sounding lines across the Challenger Deep in the 50s. This is a great book if you haven't read it, by Admiral Ritchie. He was the commanding officer at the time, and describes the process. So I think it was after the work of the latter Challenger that the area began being recognized as the Challenger Deep, but it's named after both these vessels. There's a couple more survey expeditions out to the Challenger Deep using early single beam sonars. The first descent into the Challenger Deep was by Jacques Picard and Don Walsh in the Trieste in 1960. This picture of that. Can you see my cursor on the screen?
Yes.
Okay. So this thing's kind of neat. It's just a giant float full of gasoline with shot hoppers here for ballast. I remember looking at this thing in books when I was a kid and thinking, why would you use gasoline for a float? And that gets you thinking about compressibility of gases and various liquids. So anyway, kind of neat. This was it was built by the Swiss and bought by the U.S. Navy and operated by the Navy for quite a while. Trieste is actually it's recently been moved to Washington, D.C. Here's a picture I took just a couple of weeks ago in the U.S. Navy Museum on the Navy Yard in Washington, D.C. So I'd encourage you to have a look at it if you're down here in D.C. In any case, so that was 1960. Nobody went back until 2012. There's a bit of a couple of different organizations and groups trying to get back down there. James Cameron built this vehicle, the deep sea. What was it? What it was called. Anyway, so he went down 2012, got down to the bottom, navigated around for a bit, and came back up. That vehicle was then donated to Woods Hole. It was damaged in a truck fire. I'm not sure. I don't think it's made another submergence since. So that was it. There was 2 crewed descents into the Challenger Deep, a number of survey work, including modern mapping sonars by both the Japanese, a group from UNH led by Jim Gardner, published a paper of 2014 work with the USNS Sumner. And here's just some of the various locations where folks have said, here's a measurement of the deepest spot of the world's ocean. So this is bathymetry of the Challenger Deep. This is from Cassie Bongiovanni's paper, or the data from Cassie Bongiovanni's data paper. So the Challenger Deep is really 3 distinct basins, and we've known that since the 50s, that it's not just one basin, it's 3. They're separated by quite a bit. They're separated by tens of kilometers. There's a West Basin, a Central Basin, and East Basin. And different authors over the years have claimed different depths in each one of these basins. So there's quite a bit of confusion of where the deepest spot is and what that depth is. Notably, a Russian expedition in the 50s claimed a depth deeper than 11 kilometers. That's indicated by A over here. And there's been a number of estimates close to 11 kilometers, including the work by Jim Gardner, which came to 10,980 or so meters. And another group of estimates that were closer to 10,920. And the difference between those hasn't been resolved. We'll talk about that a bit later. But anyway, so here's an example of all those are all the depths. Not all of them were claimed to be the deepest depth, but a good chunk of them are. It just shows the spread both in location and depth estimate of where the deepest spot in the ocean is. And we'll talk about this at the end as well. So this is one of the slides that's going to have some math on it. Feel free to tune out. I'll let you know when we're done. But just introduction to the hydrostatic equation and how we measure depth. So if you imagine a chunk of water, seawater of area A, delta H, the force of that thing in a gravity field is just the volume of it times the gravity times the density. If we look at a little differential chunk of pressure between the top and the bottom of that thing, that's just the area drops out, and it's just density, gravity, and the change in height. We can reorganize this thing to put the density pieces on one side that have to do with pressure on one side of the equation, and the gravity pieces on the right, which has to do with location. 1 over the density is known as the specific volume. And then if we integrate over the pressure from the top to the bottom of the column of the specific volume and integrate the gravity over the height, this gives you a potential. Noting that the average gravity, this is just the definition of taking an average of something. We can rewrite this thing to get the height of of a column of water based on the integral of the pressure integral of the specific volume divided by the average gravity. So the obviously the density and the specific volume of the water have something to do with the temperature, the pressure it's under, the salinity, and we measure that with the CTD cast, and the gravity we'll talk about a bit more has to do with where we are on Earth. So that's the hydrostatic equation. That's the equation we're going to use. Here's a typical cast. This was taken from a CTD attached to one of the landers, dropped to the bottom and recovered. Deep ocean stuff. So one thing you're going to run across, and you probably have already, if processing CTD using, say, Seabird software, a common approximation we use in oceanography is, hey, a decibar is about equal to a meter, and it is. But once you get to the deep ocean, if you're talking about 10 kilometers, that winds up being about 300 meters too deep. So here's decibar relative to the modern standard, which is the thermodynamic equation of state of the ocean, so TEOS 10, which has a handy toolbox associated with it for all sort of stuff. A lot of the literature talks about the UNESCO equation. It turns out for this CTD cast, the difference between the TEOS 10 and the UNESCO standard is not much. It's less than 10 centimeters over the full depth of the ocean. But we did have a look at that, and that caused some confusion amongst the different various authors. And then finally, and this was a little surprising, the effect of the CTD information. So the effect of the measured temperature, the measured salinity on our calculated depths relative to just standard ocean. If we just assume standard ocean, so that's 0 degrees, 35 PSU, and the pressure effects, it's not very much. And over nearly 11 kilometers of water, it's only a difference of about 8 meters to the calculated depth of pressure sensor at the bottom. So that was a little surprising to me, and you'll see how that factors into our error estimates later on. Now, that's not generally true, that this is such a small effect. Probably a decent part of that is that the deep ocean is pretty close to standard seawater. It's cold, it's 35 PSU. So the relative effect may be bigger if you're looking at a pressure sensor in, say, shallow hot water. All right, so like any good hydrographers, we need to worry about datums, and we need to talk about them. So one question is, well, okay, so you're going to measure a depth out there in the middle of the ocean. What depth? And you want to talk about the deepest spot in the ocean. What datum do we want to use? And I think intuitively, folks think about mean sea level. And so that's what we used here. Thankfully, we had a long time series of a pressure sensor that was deployed to the Challenger Deep by a group from the NOAA's Pacific Marine Environmental Laboratory. They deployed it with a hydrophone to listen to the sounds. It's a great paper on ambient sounds of the Challenger Deep. They had it down there for over 60 days. This is an image of the Coast Guard cutter Sequoia deploying that gear, or recovering, not sure which one. In any case, so that's a long pressure series, which made me think of, hey, I've got a tide station out there. There's quite a bit of drift. This orange is the raw pressure from the sensor deployed on the seabed. The blue is the water level record at Guam. There's a NOAA tide gauge in Guam. We were able to take the drift out and then calculate, just using traditional tide by tide analysis, the amplitude and phase offset for the tides at the Challenger Deep relative to Guam. It turns out the tides are bigger out in the middle of the ocean. They're 20% bigger than they are in Guam, but with zero phase offset. So that was nice. We were just fortuitously, we happened to have a data set available that let us establish tidal datums out at Challenger Deep. So that's what we use for control for vertical control during the actual dives, or in processing the data for the dives. And that lets us get to measurement relative to mean sea level. All right, so gravity. Gravity is a big piece of this, and something we wound up spending a lot of time thinking about. So gravity on the Earth and gravity under the ocean. So the gravity model in the UNESCO equation in TOS 10 is GRS-80, which is a model of a uniform rotating ellipsoid Earth with a uniform liquid ocean on it. Somewhat surprisingly, so the gravity changes quite a bit. The big one is a factor of latitude. If you want to lose weight, go to the equator. So if you weigh 201 pounds on the North Pole, you'd weigh 200 pounds on the equator, just because you're a little closer to the center of the Earth on the North Pole and the rotation of the Earth. The other piece, and this took a little more head scratching, was as you go, if you imagine starting from outer space and approaching the Earth, the gravity increases. You're getting closer to the mass of the Earth. So that's the 1/r² stuff. But then as you start penetrating into the Earth, either going beneath the ocean or beneath the rock, you've got a lot of mass on top of you pulling you up, or similarly, there's just less Earth underneath you pulling you down. So the gravity changes as you go into the Earth. The gradient of gravity with respect to depth that's embedded in the GRS-80, and McDougall in his notes with the TOS toolbox also notes this, that it just sort of came out of thin air, this gravity gradient. You can derive it, and we do that in the paper that I'll show you in the end. And that gravity gradient is essentially assuming a shell of typical seawater over the Earth. So the gravity, as you descend into the ocean, the gravity still increases, but less quickly than it does if the oceans weren't there. One question we had is, okay, well, I get that, and that makes sense. Is as we descend into this ocean, I understand how all this math works, and that's great. But the average depth of the ocean is only about 4,000 meters, and as we at the bottom of the Challenger Deep is close to 11,000 meters. So at the bottom of the Challenger Deep, you're actually under more rock than you are ocean. So does it make sense do we need a different gravity gradient? And so we thought about this, and I thought, well, boy, we've got bathymetry. It should be pretty easy to just calculate the gravity everywhere. It turns out that's a really difficult problem in geodesy. That's a downward continuation of gravity problem. I had many fruitful conversations with Walter Smith, who of the Smith and Sandwell model, about the difficulty of doing this sort of thing. And the other thing in thinking about this is there's gravity anomalies that are calculated, and Smith and Sandwell happen to have prepared one. And here's the gravity anomaly. So relative to the GRS-80 surface gravity over the Marianas Trench, you can see this is Guam here, Saipan, and this is the trench. There's a big deficit of gravity over the trench, obviously because there's a big hole in the ground, and we're missing a bunch of rock that would be pulling us down. It wasn't clear to me though, does that fully capture, does the surface anomaly, does that make sense to use? How do we associate an error term with this gravity correction? And we did a couple of just bounding case models once I learned that, or discovered that it was going to be really hard to do a decent calculation. So I tried to just bound this, modeled the Challenger Deep as, okay, it's got to be between these two end states. One end state would be, we've got a Earth that's got 4,000 meters of ocean, and beneath that is the solid rock of the Earth. So one model would be, I'm just going to take a slab, an infinite slab, nearly 7 kilometers deep of rock, take that out, put water in its place, and calculate the gravity effect of that. So that would be one bounding case, whereas the Challenger Deep is just a big, infinitely large hole in the earth, infinitely wide. And the second bounding case is if we imagine going down to the seabed at 4,000 meters and then just drilling a hole straight through that rock. So it's got to be somewhere in between those two. We also modeled a cylinder. Why these things is you can analytically calculate the gravity effect. So this blue case, so this is if we imagine calculating a depth from pressure and correcting for this gravity, the blue case would be the missing slab model. The green case is if modeling the Challenger Deep is a hole bored in solid rock. And then this black piece, this black line here is using the surface gravity anomaly and gradient anomaly. And it was satisfying that this answer is between these two end cases and gives us an idea of what the error the maximum possible error, right? We know the Challenger Deep is certainly not an infinite slab, and we know it's certainly not just a hole bored in rock. So it's somewhere in the middle here. The orange line was a intermediate model of a 10-kilometer radius cylinder stuck into the seafloor. Anyway, so that lets us take into account the gravity effect of basically the giant hole in the earth that the Challenger Deep is, and that's a surprisingly big effect. As you can see here, that's about a 4-meter correction, which is about half the correction from the effect of accommodating the CTD information. So that's gravity in the sea, and that's an additional correction we use to accommodate the difference of in situ gravity from the model gravity. So here's a schematic of the vehicle itself, and I want to emphasize I had nothing to do with building this vehicle, putting any instrumentation on, paying for it. We were brought in solely to be an independent look at the data and an independent calculation of the depth. I was brought in when Victor went back to the Challenger Deep. One of the folks who went back with him was Kathy Sullivan, former administrator of NOAA. And so she contacted NOAA and said, "Hey, NOAA, could you help? Could you be the independent? Could you help make this calculation? This seems in your wheelhouse, figuring out how deep the ocean is." NOAA said yes. Rick Spinrad asked co-survey. Figured, okay, you co-survey guys know how deep the ocean is, and the director of co-survey, Shep Smith at the time, called me up and said, "Hey, can you help these guys with this calculation?" So that's how I got roped into this. I had a bunch of fruitful conversations with Chris Mining at the Pacific Marine Environmental Lab, who has a tremendous amount of experience with deep ocean sensors and deep ocean pressure sensors in particular. So this is a vehicle. The little ball is where the people were, and then flotation, weights, and right on the bottom of this thing was an altimeter, a short-range altimeter, and also a CTD that had a pressure sensor installed. So this is a cartoon of how we got profiles of the seafloor. For each dive, they dropped landers down in advance of the vehicle, and those were used for navigation on the seabed. They had acoustic ranging modems on them. So typically the vehicle would rendezvous with one lander and then go to where the other lander was, and using that for underwater navigation. Each lander had a RBR pressure gauge on it, as well as the CTD. We used the profiles up and down to look at the water column. And then that RBR pressure gauge was far more accurate than the pressure gauge on the CTD and on the vehicle itself. And because it was deployed for many hours, it was useful to use that lander. So we used that to basically establish benchmarks on the seabed that the vehicle would then tie in with and locate the altimeter record in a absolutely referenced frame relative to mean sea level. This is just an example. We did have to pull drift with deep sea pressure sensors is a challenge. And so this is an example of one of the landers on the seabed for around 7 hours. There's a bit of a bilinear drift that we pulled out. Not huge. It's only about a meter, but the calibration was all done at times in the pressure sensor in the pressure chamber at much less than an hour. So we figured this was an appropriate treatment. It was nice having the pressure sensors sitting on the seabed. Let us make sure that we're pulling out the tide in the right way, the atmospheric loading, all the by having a nice stable sensor on the seafloor. So this is an example of a profile from one of the dives. The red triangle here is where the lander was and where the altimeter record, we tied in the altimeter record. So the black line is the vehicle height. As you can see, they're maneuvering up and down as they maneuver over the seafloor. This is just time. We didn't have any location. It's just pure time so as they maneuver along the seabed. All right, so answers. So how deep is the ocean? These were the 6 dives that got down to the bottom of the pools, shown with the lander ties. So the profile of the seabed, it's not, we can't unambiguously tie that to distance, because it depends how fast the vehicle is moving on the bottom. But you can see that while some of this area is very flat, there is topography at the bottom of the ocean. Not very big topography, but it's certainly not flat as a pancake. So here's a little detailed bathymetry. Again, this is from Cassie Bongiovanni's data. So data from the support, mapping data from the support ship overlaid with tracks of the vehicle on the seabed. We saw the deepest depths in the eastern basin of 10,935 meters. The western basin was nearly as deep, 10,933, and certainly within the estimated error of our measurements. Those errors are at 1 sigma. And the central basin appeared to be a bit shallower at 10,922. So here's where that error term comes from. Here's the corrections for each of the terms plus the associated uncertainty. Just the raw correction, the raw pressure measurement corrected for raw pressure measurement was 10,922. The correction due to the dynamic height anomalies, that's the correction due to the measured salinity temperature of the profile, is a little over 8 meters. And the uncertainty of that we estimated a couple of different ways, but it's not very big, and that was a surprise to me. We looked at that using Monte Carlo methods. The gravity's kind of a big term, nearly half as big as the correction from the CTD. And the uncertainty there is kind of big too. Again, nowhere near the uncertainty of the pressure sensor itself. That dominates the overall uncertainty. We also looked at atmospheric loading. So to come back to the various other estimates of how deep it was, or how deep the Challenger Deep is. So here's a number of them that we pulled out that did claim that these were the deepest observed spots. The ones highlighted in red, we just can't reconcile to. The ones in green, we argue that our answers are consistent with those measurements. For example, the Trieste dove in the western basin, they observed a depth of 10,910 meters. The positioning was relatively crude. The B little triangle over here is the reported position. Clearly, they weren't there because they got down a lot deeper. This is the 60s. They didn't specify their positional uncertainty, but it's possible that their positioning in the global frame was largely done with celestial navigation. In reading the account from Don Walsh and Jacques Picard, they located the depth for the dive, they had one of the support ships driving lines with hand-tossed explosives off the back. And when they found a deep spot, they marked it with flares, and then that's where the Trieste was towed to make its descent. So a little crude from the positioning standpoint. In any case, the an expedition with modern mapping sonar we agree with within the reported uncertainties of 10,925 in the Western Basin. We don't agree with the estimate from Gardner and other researchers from UNH from the 2010 survey from the Sumner. It's just too deep and 10,984. And we'll talk a little bit about some of the things we looked at to see if we can understand where that difference came from. And similarly, in the Eastern Basin, there's a Japanese expedition in the late 1990s, that again came up with a 10,900, a lot closer to 11 kilometers. And there's the Deep Sea Challenger is James Cameron, 10,908. It certainly seems that the Deep Sea Challenger and the current mission, so these are the depths from the current mission, the vehicle's name was the limiting factor. They certainly look like they went to about the same place. So my guess is the differences between those depths are due to instrumentation and processing differences. Interesting, this is a recent paper. The measurement was made in 2014 by Scott Loringer, UNH's a former student here, out or there, which a great paper. I highly encourage you to read it. They had instrumentation, one of which blew up. It's imploded at depth, but Scott was able to use that pressure, the bang from the exploding instrument, and as recorded on a different instrument, to make an estimate of the depth of the Challenger Deep. He came with an answer very close to 11 kilometers. We worked on, I'll get to both Scott and Van Haren, who was on the Somme, suggested that perhaps these other measurements that were coming closer to 11 kilometers were due to the difference in sound speed, but they didn't calculate it. We calculated that, and it's not sufficient to explain. Also, the location of Scott's implosion is not coincident with the known areas. So I suspect that this might have some multipath or some non-nadir returns. And this is just a qualitative look at the various profiles, sound speed profiles used. We were able to get them for one of the Japanese expeditions, the Gardner work, from Van Haren, he was on the Somme, and Scott Loringer shared his profiles as well. There are differences in the harmonic mean, but the depth difference, Gardner used the fastest profile, is not sufficient to explain the 50 to 60 meters difference, nor are the different equations for sound speed that the various authors have used. So that remains unexplained. So the paper, we published this paper laying all this out last year. Kathy Sullivan joined. The other authors were officers with me on Rainier. This was a wonderful project to do during the pandemic when we were otherwise tied up. So why it's interesting, I think that it's the deepest spot in the ocean, right? And if your business is measuring how deep the ocean is, it's kind of an interesting thing to do. But it's also interesting from the advances in pressure sensors. The pressure sensors we used, we estimated uncertainty of 3 meters. There's pressure sensors out there now and that are in development that could be far more precise than that. And that opens up all sorts of applications, not only measurement of water levels, measurement of depths, but also understanding the properties of the ocean. And one interesting application, if you imagine a pressure sensor on the bottom of the ocean and then heat up the ocean expands, sea level rises, but the pressure on the bottom doesn't change. So the sea bottom pressure is an interesting measurement or calculation for teasing apart the differences in sea level rise between the steric effects of the expanding ocean and just more water in the ocean from melting ice. So I think the detailed calculation of rather than just applying the UNESCO equation and writing down a number, of really thinking through the whole measurement of depths in the ocean with this level of precision, it may be useful for any number of applications going forward. I was surprised to find that gravity, if we get a better pressure sensor, and there's ones out there now that are in development, the thing that we're going to need to sharpen our pencils on first is not the CTD measurements, it's the gravity. We need to better calculate gravity throughout the ocean. There's been some promising work on that on the terrestrial side, but I haven't seen anything on the marine side in terms of doing those global calculations of gravity throughout the ocean. So that's all I've got. Happy to take questions. I think I got about 10 minutes.
Sam, if I was looking at the profiles from the submersible, it looked like there were small features that went deep that I suspect are not resolvable from the surface multi-beams. Is it conceivable there's actually a deeper spot, just too small to resolve?
Good question. So there certainly are features on the seabed, and that's exciting to see. A lot of the reports from folks who've been down there or been down there with ROVs is, hey, this thing's flat as the Bonneville Flats, and it's pretty flat. I mean, the units there are not very big. Is it possible there's a deeper spot? Yeah, until you map the whole thing at a higher resolution, sure, it's possible. Whether that's physically reasonable given the sediments and the type of stuff that's down there, that there's a missing 50-meter deep hole, I don't think that's likely, but it's possible. I would love to see a multi-beam survey of each of these basins, right? Which would require putting a depth-rated multi-beam down on a vehicle and surveying it. So sure, possible. How possible, I don't know.
I have a question. Sure. You said you used, was it 16 CTD casts? Well, there was, yep. So every lander had its own CTD. Yep. Those were not as accurate as the CTD on the submersible itself?
No, so each lander had a CTD on it, and the submersible had a CTD on it. So we had a lot of CTD casts. And it turned out that the observed variability, was comparable to the expected error in the measurement anyway. So it just wasn't a big part of, the variability of the observed cast wasn't a big part of the puzzle. What I meant was, so we were using the pressure sensor on the CTD on the submersible to control right, you have to locate the vehicle as it goes up and down to reference the altimeter record. So we're using that as sort of local control and then tying that CTD into the lander when it rendezvoused with the lander to get to absolute control relative to mean sea level.
Thank you. Anyone else? Oh, okay. Jack, and then Walter.
So to model the gravity, you use the like a model of a core of water surrounded by rock. What is the width of this kind of basin at its deepest point?
Good question. Let's look at the picture. So that's the last 1,000 meters is probably about 10, 15 kilometers across. But overall, the overall profile is, it's a complex, more V-shaped thing. What we were trying to do there was justify. My question that we're trying to put bounds on is, if I just use the surface anomaly, the surface gravity anomaly and the gravity gradient anomaly at the surface, is that reasonable? Is that even within bounds of what I might expect to happen down here? Or do we need to do more sophisticated analysis because this thing's so far under all the rock, right? From in a global sense, because it's under more rock than ocean. Is that good enough, or do we need to do more sophisticated modeling? So the point there was, okay, it's somewhere between these bounds. That's reasonable. But if we want to get that error term smaller, we certainly need to do a much better job of modeling the gravity or measuring it, putting a gravimeter in the sub all the way down.
Walter?
Actually, that's exactly the question I wanted to ask you. I'm from Ifremer and actually in France. Someone is trying to develop a much smaller gravimeter, which could be on the Nautil, which is our manned submersible. So I was thinking of, if you were considering that, it would be a good idea to lower a gravimeter actually and measure, because I've been dabbling in this field and I know downward continuation below rocks is extremely complicated. The measurement would be the right solution.
Yeah, I'd love to. And again, I'm just processing the data. This isn't my sub. It's not my instruments. I didn't come up with a plan. But absolutely, if next time Victor goes back there and says, hey, can I take any instrument? I would say, rather than taking somebody with you in the co-pilot seat, can you put a gravimeter in there and strap it in? I would love to see in situ gravity all the way down.
Yeah.
So if you were to design a mission yourself to go get like gold standard of measurement down there, what would you do differently aside from taking the gravimeter with you?
So there's to get better, there's better pressure sensors available now that were in development, I think, that that deal with some of the drift. So I think A would be improve the pressure sensor a bit. I think the technique of putting a lander on the seafloor really helped in a number of ways, just to make sure, because we know it's stable in terms of evaluating drift and make sure the time corrections, make sure we got the tide out of it right. So that would be one, is the pressure sensor. Two would be, if unlimited resources, if I could have a gravimeter go down with it and actually measure the gravity field. And then three, I'd get a better acoustic sensor. I get a multi-beam and see if we can survey this whole thing. Would be really cool to see. This is the bottom of the ocean. This is two plates grinding together. What does the bathymetry look like at a higher resolution? Would be really neat.
What's the seabed type down there?
I think it's silty. Silty mud. There's a number of other papers about the critters that live down there from other investigators, but I think it's pretty silty.
That lander's pretty stable then, even if it's soft?
Yeah, it's a good question. Is it slowly sinking into the sediment? The drift that we saw on it, if it weren't drift of the instrument, would have been the instrument coming out of the seabed, which didn't seem reasonable. But a good question. It could be unstable on the seabed. So 10,935 meters is how deep the ocean is, plus or minus 3.
Yeah.
And where? So we measured the deepest spot in the Eastern Basin. But again, this Western Basin is almost as deep. So I think the where is the deepest spot in the ocean I would say it's a tie between those two in any objective sense, which is pretty amazing, right? Here's the deepest spot in the ocean and we still don't know where it is. But it's a lot better constrained now. All right, thank you, everybody.